Video. Google. A warm welcome to our program. Just wait for 5 minutes, couple of minutes, because students are joining.
Okay, sir. Okay. Sure, sir. Good afternoon, sir.
Google, is it audible?
Yes, sir. I audible, sir. Am I audible, sir?
Madam, but your voice is very low, madam.
Sir, am I audible, sir?
Yeah, it is good.
Yes.
Your volume is a little bit lower.
Sir, now am I audible?
Yeah. Yes, madam.
Okay, sir.
Just wait for 5 minutes. Students are joining.
Sure, sir.
Good evening to all. Hello. Madam Pogololi, madam, is it audible, madam?
Yes, sir. Yes, sir. Yes, sir.
So, on behalf of our Vivekananda College of Engineering for Women and our Vivekananda Innovation and Startup Center, so along with our Institution Innovation Council, we wholeheartedly welcome our today's speaker, Ms. Pogololi, madam, from SRM University. So, he is a AP IT, well experienced person, and also he is a very familiar in computer communication. So we wholeheartedly welcome once again our madam to
Thank
deliver
you,
the
sir.
topic to our students. Welcome you, ma'am.
Thank you, sir. Thank you. Shall I start, sir?
Yes, madam, you can start, madam.
Okay. Good afternoon for everyone. Myself, Puhurali, I am working in SRM as an assistant professor. Today, I am going to talk about capsule network. Capsule network, this term seems to be very rare. Most of us have not been heard about that, but we have heard about neural networks, convolutional neural networks. But capsule network that emerged during 2017, but it is more actually we are using the neural network concept for this. So we will see what is the main advantages of using our capsule network and how it is addressing some of the issues in the neural net CNN. One second. Slide. Sir, my screen is visible. Sir,
Madam, yes, madam, visible, madam.
okay. Yes, sir. Thank you. So, capsule network was introduced during 2017 by Jeffrey Hinton, and he named this as capsules. We know that what the actual capsule contains. We will see how these capsules are working better. And he published a paper on the routing algorithm, that is dynamic routing. Okay, we will see what is the dynamic routing and why this name is called the dynamic routing and how it is applied in our convolutional neural network. Okay, we all know about convolutional neural network. I'm just giving the overview of this. So we know that the main component of the CNN is convolutional layers. So we will be having the input. The input is represented as a matrix. That matrix range the values. Okay, that values ranges between 0 to 255. If it is a RGB, that is a color image, then we will be having the 3 channels, RGB channels. Okay. So the main job of your CNN that detects the features and learns the color gradients, textures, detect the edges. Okay, it extract the features actually. So that will be grouped into the feature maps. So this is what actually the CNN does in the middle layers. Okay, after getting this, extracting these features from the input image, then what it actually does, it classifies it classifies the image. If you feeding a cat image or the dog image, it classifies and it says, yes, this is a cat, this is a dog. How it is classifying this? So it is based on the features which is extracted from the particular image. Okay. So this is the overview of our CNN, which we all know that. So here in CNN, there are we have the ReLU, sigmoid. We might have heard about that. So I'm not going in depth of anything else, but I'm just giving the overview. Okay. This is okay. The main drawback. We'll talk about the main drawback of our CNN. So if you are feeding an image, okay, it is extracting the features that we all know that. So extracting the features in the sense, okay, this particular picture has a eyes, nose, mouth, ear, and this is the shape of your face. So these are all the features it will extract. So for the CNN, these two pictures doesn't seems to there is no different. So if you feed the first picture, it will extract the feature, that is the shape of the face, the eyes, nose, and the mouth. And here, if you feed the second picture, the same thing going to happen. So for the CNN, both the pictures are same because the features, it extract the features. But what happens? Suppose if you want to know about the pose, that is the orientation and the position of the particular feature in your image. So CNN does not concentrate on this, that is the pose, on the orientation, and how much angle. Okay, so if you imagine the different angles, the CNN failed to capture that. So it does not pay attention on the orientation and the pose. So that is a main drawback of your CNN. Okay, then later comes your max pooling. So they have used the max pooling in the CNN. What the max pooling will do? So consider you have a RGB channel. Okay, you have a RGB channel, and consider only this part is represented. So this is the window. Only this is a 4x4 window that is represented here. Okay, in this particular window, the maximum value will be extracted. What the max pooling will do, it will extract the higher order features. So what is the maximum value here in the R channel? 9. What is the maximum value that we could able to see? That is 6. What is the maximum value that is in the B channel? Here, 9. So that is the max pooling. Max pooling, what it does, it will extract the higher level order. So, okay, when I am using in the first layer, okay, I have extracted. What about the rest of the information? Almost the rest of the information will get lost when I am moving on to further layers. Further layers, if I am moving, at the time my important information will be lost. And it will not capture any spatial information. What is that spatial information mean? Spatial information is nothing but your hierarchical representation. Suppose if you are taking the face, in this particular position only our eyes are located. In that particular position only our nose are located. Okay, so the spatial information, the relationship between them are lost. So that will not be handled by our CNN. So here I have given a picture. So in a different pose, okay. So if consider if I am feeding the second picture. So what our CNN will do, it will extract the features. Okay, this is a as a human we know that this is a liberty statue, but what are the features it has? From the top to bottom, it will acquire the features like your lamp, book in the hand, everything. So what I am giving the different pose of another orientation of your liberty statue. At the time, our CNN consider that is a different picture. So here the main drawback is that pose and the orientation will not be recognized. The CNN will not pay attention actually. So that is the main drawback of our CNN. So here, so previously we have seen a face picture, right? So it will estimate the probability of each and every features it extracted. So this is how the CNN will classify the image. So this main problem will be addressed. This disadvantage of the CNN will be addressed using the capsule network. So what the capsule network will do, actually capsule is a group of something that we all know that. It is a group of something. Actually, it is holding the neuron. It decodes the spatial information and detects the presence of the object. That is where it is the location and the orientation of the particular object. But in the CNN, the location and the orientation will not be captured. So let's see. Here, one example I have given. So when I am giving the first row of image. So what actually the CapsNet will do, it will acquire all the information, that is all the features of the particular object. So first object is lion, for example. If I take, it will capture all the features at different orientation, different angles. So that is the main advantage of the CAPS network. So next time, if I am feeding the second row image, at the time my CAPS net able to detect that particular image. Okay, this is the lion. If I am giving the top angle, or if I am giving the side angle, if I am giving at the back angle, my CAPS net able to do that. So they have implemented and they have achieved that. But the main advantage of the CAPSnet is it does not require any lot more data for training. It requires very small amount of data for training. Within the small amount of data, it could able to recognize the object at the different angles. It could able to recognize object at different angles, and also, so we will see some of the examples how it is actually recognizing. So mostly in so why, okay, I will tell you why this concept coming to in the mind of Geoffrey Hinton, because when we are seeing any object in the real time, so actually we are seeing an image and we are decoding it and we are deconstructing it, and because deconstructing, and then we are identifying okay, this is what the board, this is what the chair, how we are concluding that. So already we have learned from the real-time example, and we come to know that we have stored that pattern and the representation of the object, and for a boat, how the location of each and every objects present in the boat are located, isn't it? So likewise, so whenever this is similar like our human brain. This is similar like our human brain. So actually our human brain does the opposite of rendering. That is inverse graphics. Actually it sees an image, deconstruct it, and then try to match it with already learned patterns and the representations that is stored in our brain. Actually this is what it is acting. So having this idea, Geoffrey Hinton came into this CAPS network. So in the computer graphics, if we are feeding this information, like these are called the instantiation parameters. I'm providing XY parameters and angle, how it has to be tilted. And likewise for the triangle, I am providing this information. And finally, I am rendering some image. So this is actually, we are rendering one image in the computer graphics. What is the reverse graphics? That is the inverse graphics. So inverse graphics means from the image to, I need to identify, is my screen?
Madam, screen is not visible, madam.
Yes, sir. 1 second, sir. Okay. Actually, our brain is doing the inverse graphics, that is inverse rendering. From the image, it is deconstructing its parameters and identifying what could be its X and Y parameter and how much it is get tilted. So these information are getting extracted from the image. So from this idea, your capsule network. So from this only he built the capsule network. So capsule network is nothing but actually a neural network that performs the inverse graphics, and it composed of many capsules. It composed of many capsules, but a capsule network uses the convolutional neural network concept, but not the max pooling. And capsule means we know that it is a group of neurons that output some different properties. So we have seen the lion object, right? So in that is the same entity, but it has the different properties, and it predicts the presence. And so here, based on the example which I have given, so the capsule is any function that tries to predict the present and the instantiation of parameters of the particular object at a particular in a given location. So the capsule network that contains several set of capsules. So already we know what is capsules. Once again. So it is reusing the output from several of those capsules. We will see from the one example which I have in the further slides. So, okay. So here is my image. Here is my image. I am doing the inverse rendering, and these arrows are representing the activations These arrows are activations, and this I can call this complete thing as a capsule. And that is, a network contains the capsules, and the capsule contains groups different neurons, and these arrows represents the vectors of these capsules on directions. We can say the directions, and the black arrow corresponds to the find the triangle, I think, sorry, rectangle, and the blue arrow represents the that is the output of the capsules looking for the triangle. Actually, it is trying to find out for the output vector output. Okay, so these are the capsule activations, and here what is this many minute vectors, I can call this minute activations are. So it means that the minute arrows, that is minute arrows that represents, actually the capsules didn't detected anything, but the two arrows are quite long here. It means that the capsules at this particular location. So this is the actual image. So likewise, okay. So in this empty spaces, are represented with this tiny arrows, and where the image is actually present, that is represented with the large arrows. So this capsule at these locations are they very, very pretty confident that they have found what they are looking for. Okay. So here, so that is what it is represented as the larger arrows. So here that activation vector is nothing but the length is estimated with the probability of the presence. So it is presence. Okay. So in this previous diagram, if we see, we have the small arrows. It means that it is not found. The length of the arrow, okay, that is the estimated probability of the presence. There, the image is there. In that particular location, the image is there. And orientation, the pose, in what angle, the object estimated pose parameters or the orientations. So these two combined together called the activation vector. So I can say the object rotation, its thickness, how much it is stretched, that is the 3D parameters of the particular object, where it is exactly located. So obviously we are using here the convolutional layers in the initial stage. How we so in practice, if we use the convolutional layers, just like our CNN, so the first layer, it will output the certain feature maps. So it will extract the features. So that is called the feature maps. And we can reshape this array to get the set of vectors at each location. That is what actually we do. So what about this squashing? So here reshape is the what is the array we are array means that is the feature maps we are getting at the particular locations. And what about this squashing? So squashing, so obviously the main advantage of this particular CAPS network is it preserves the orientation of the particular image. So actually what it does not change its direction. The squash function, so actually like in your in our CNN, we use the activation function. Here we are using the squash function. In a simple meaning, I can say comparison between our CNN and here, the squash function is similar like our activation function, but it does not change any direction, but it maintains the range between 0 to 1. Actually between the 0 to 1. So here two vectors that is representing this boat image. Actually consider this looking like a boat image. So here I am having two vectors here. So at each locations it is represented with the two vectors. Okay, but the length determines the presence of the particular object. So actually this squashing preserves the vector orientation also and maintains the range between 0 to 1. And here, the main advantage, one more thing. And one more thing, The main advantage of the CAPS network is the equivariance. Equivariance means the main feature of, this is the main feature of your CAPS network. They preserve the detailed information about the object location and pose. That is what the main advantage of your capsule network. That term is called the equivariance. And suppose if I am slightly changing this, changing the pose of this particular image, all these activations, sorry, capsule activations also changes. All this activation also slightly changes. So this is called the equivariance. So in regular CNN, we uses the max pooling, but unfortunately, this loses the most important features. But here, this preserves all the information. That is orientation, pose, how much it is stretched, all this information are preserved here. And one more important thing about this CAPS network is, here it learns by dynamic routing, but in the neural network, the network learns by the backward propagation, back propagation, updating the weights. Here also the concept, we have the weight updation, but the difference is CAPS network learns by dynamic routing. In neural network, that is done by back propagation. So consider here we have a primary capsule. Okay, so actually we are having a triangle and the rectangle. So the same thing, using the triangle and the rectangle, I could be able to draw the house. I could be able to draw the house. But how this capsule network able to differentiate, this is the boat, this is a house. That is a very challenging part. That is a very challenging. So here, first thing, we are using the couple of convolutional layers. So I am using convolutional layers here. And second, I need to reshape the vectors. That's what we have seen, reshape and squash. So third, I need to squash. So these are the main steps of your capsule network. So this all together three will result in our primary capsule. So this is how the primary capsule will look like. So it has the small arrows and the lengthy arrow. Lengthy arrow represents the thing, the presence of an object. So every capsule in the first layer try to predict the output of every capsule in the second layer. That is the next upcoming layers. So the first layer will predict the output of the second layer. The second capsule try to predict the output of the third capsule. So likewise, it will goes on. Okay. So first to see, we have represented the blue arrow as a triangle and the black arrow as a rectangle. If you see here, we are first considering the black arrow. So the black arrow has this orientation, and so I am having a set of images. Okay, so see, I predicted two images which are having the same orientation of my rectangle. Okay, next I am moving on with the triangle. In the triangle is somewhat tilted from the rectangle, but here I am considering only the triangle. So here also I have a tilted triangle. I am having a tilted triangle. Okay, so next, so after having this, I am having four predicted outputs. So primary capsules, here also I can say I'm having a tilted triangle. See here, this triangle also tilted and this triangle also tilted. So I could able to see four predicted outputs. From this, I need to say this and this belongs to the boat. and and not this. Okay, so how can I do this? So here comes the concept called routing by agreement. So how it is actually done? So the rectangle capsule and the triangle capsule really occurs like a boat shape, and there is no need to okay, based on the orientation and the pose, the routing by algorithm detects this particular two images are belongs to the boat. So it is agreeing strongly. What it actually does, it is discarding this information and it is sent to the other capsule. The capsule which is only meant for boat. This is boat capsule, for example. So this strong agreement, after agreeing this, okay, these are rectangle and a triangle are represented with similar to the boat, and it is agreeing strong and it is sent to only the boat capsule, and the rest of the two pictures are discarded. So it thus avoiding the ambiguity. So sometimes in the same picture, I may be having a house type and the boat type. See here. So I could able to see house type and the boat type. So I need to handle this crowded scene. So both are represented with the triangle and the rectangle. We need to identify this. So how can we do this? So here, if you see, your house, sorry, boat is represented with black rectangle, and the triangle are represented in the down, and for the house it is represented in the top of that. So after that, this boat is represented in the down part and the house is represented in the top part, but actually we are doing predicting the boat from the image. So what we need to take, the length of the longest arrow will be considered, and thus we are avoiding the ambiguity. So this routing algorithm avoiding this ambiguity and thus resolving this problem and identifying, yes, it contains, this is a house and this is a boat. Why? Because our CAPS network's main advantage is it is able to differentiate the images occurring its different properties of a particular entity at different angles, and its locations are preserved here. So based on the location and the orientation, it is very easy to plot or predict the particular object in the image. So the main advantage of this capsule network, so it reaches its utmost accuracy, like 99%, 99 point something accuracy on MNST data, and very less training data is required. But the main disadvantage is if we are feeding with the more complex data, that is more data are done. So it is taking too much time and it couldn't able to do the training process. And position and the pose informations are preserved here, which is we called the term called the equivariance, and it is very, very promising one for the image segmentation and the object detection in the real time. So routing by agreement is a very, very important for the CAPS network that prevents the ambiguity of overlapping objects, which we have seen for our house and the boat. So here we are using the capsule activations that maps the hierarchy of parts. Hierarchy of parts means, so the relationship between our face and the nose, for example, I can say, where it is actually located. And robust to affine transformation and translations, spinors, stretching, pose, orientations. So activation vectors are easily to interpret. Here also we will be doing weighted sum calculations, squashing functions instead of activation function of the neural network. We are doing here the squash function here, and so it is almost we are using the convolutional network concept here for our CAPS network. And main drawback here, They have implemented this CAPS network on CIFAR 10, but it is providing less than 10% accuracy, which is not meeting its state of art. And on large database or the larger images, it has not been applied it. And it is very, very slow due to routing by algorithm, routing by agreement. Why? Because so once we have detected the house or this boat, if I need to detect only boat, so this will be fed to next capsule, only for boat capsule. And again, this information will be moved on to further layers. So the loop will be moving on in the inner loop, or that is the inner loop will be running for one particular image. If we want to detect a particular image, in that particular image, only the dynamic routing loop will be moving on. So that's why the training is very slow here. Otherwise, it is very much providing high accuracy. So here I have provided the architecture of the CAPSnet for MNIST data, which predicts the digit. So we can call this as digicaps. So many mathematical concept comes in behind the picture. So here everything is primary caps. So likewise, first we are using the convolutional layer. As I said, we have a convolutional layer and we have the primary caps. So here itself we will be having convolutional layer. Then we are doing our reshaping, and then squashing comes here. And the output will be fed into our primary capsule, which we have seen in already one example. And the primary capsule will further, it will send the information to next layer. So actually the CAPSnet architecture, I'm just drawing here. So this architecture CAPSnet has two divided into two, that is encoder. Initially we have seen about the encoding the spatial information, that is done by the encoder, and the decoder is built upon this CAPSnet. So here in the encoder we have the convolutional layer. I'm just writing con layer. Then we have a primary caps and digicaps. In the decoder, we have the fully connected layers FC1, FC2, FC3. This is actually similar like our CNN. Only thing, they are some terms are different, and we are grouping this information, and we are preserving the orientation, pose, skewness, thickness. So all these spatial informations are preserved here. So actually how the CAPSnet works here. So your U3 here mentioned U3, that is the vector output of the nose. So U1, consider U1 is the eye, U2 is mouth, U3 is the nose. And that encodes the existence and the pose of the nose. And W3J, W2J, W1J, that is the weight matrix. And U1 cap, U2 cap, and U3 cap are the matrix multiplied output. That is a dot product of U3 and W3J, U2 and W2J. So that is the dot product. And here C3 is a scalar weight, which is determined by our routing, dynamic routing. And here we use the squash function. In the neural network, we use the activation function and sum of weighted function. And this is our vector output of phase, and it encodes in the particular phase where is the existence of the nose. Okay, for example, I can say like in a phase Where is the existence of nose? Where is the existence of the eyes? Where is the existence of the mouth? So that is our UJ. So this is called our phase capsule. This entire thing is called our phase capsule. And this is the difference between our traditional neural network and the capsule network. So here we are using the affine transformation, and we are using weighted sum of weighted sum. And here we are using the non-linear activation, which is our squashing function. And here for the CAPSNet, we receive the output as a vector, but in the traditional one, we are receiving output as a scalar. And this is a diagrammatic representation of the conventional neural network and the CAPSNet. So thank you, sir. Sir.
Madam?
Sir, yes, sir, I am completed. Thank you for this opportunity. Any questions?
Students, we are having any queries regarding your today's topic? You can ask our madam. Hello.
Sir?
Yes, madam. Ma'am, today we have a wonderful session. That is advancement of our computer networks, so which is called as our capsule network.
Okay. Thank you.
So thank you for your wonderful session, madam.
Thank you, sir. Thank you for giving me this nice opportunity.
Yes, madam. So on behalf of our Vivekananda College of Engineering for Women, so we need to you are kind enough, and also we need to your support, madam, for further
Definitely,
activities.
Definitely,
So keep in
sir.
touch with us. So we'll meet after opening of our college. Definitely we'll invite you for just lecture, madam, to our college.
Definitely, sir.
Yes,
I will be providing my
some other topic,
presence.
madam, like our today's trend is big data and AI. So we'll talk about that, madam, in later sessions.
Definitely, sir. I will be there.
Yes, madam.
Yes,
So
sir.
once again, thank you, madam, for on behalf of our way and the College of Engineering for Women, madam. Thank you.
Thank you, sir. Thank you so much, sir.
Yes, madam. Thank you, madam.
And thank you all for watching this and being passions. Thank you so much for giving me this nice opportunity.